Welcome everyone to the 13th and last vetting session on the COMNET Modeling Guidelines and Procedures. Today we're going to address Chapter 7, which is a kind of a different type of chapter for COMNET. The other chapters are mostly deal with software specifications, requirements for software. Are really tips to the modeler on how to deal with challenging building types, advanced design approaches and technologies. This chapter is really divided into two parts. The first part addresses challenging building types like laboratories, um, healthcare, and data centers. These building types all present special challenges for energy modeling, and COMNET has some guidance on how to deal with these. As we get started, I just want to note that with regard to healthcare, laboratories, and data centers, there's two exceptions to the HVAC mapping rules that apply to all of these cases, and I want to point those out and explain them. The first exception applies just to laboratories, and any laboratory that has 5,000 CFM or more of exhaust. For such laboratories, they should be modeled in the baseline building with a separate system, either system 5 or 6, which is a packaged VAV. The difference is the heating source. So that's the first exception. The second exception is a more general exception. It applies to any type of building, and what it says is that separate systems, either 3 or 4, which are basically single zone rooftop packages. 4 is a heat pump and 3 is a furnace. Are used for spaces when they have a heat gain difference of more than 10 BT, more than or equal to 10 BTUs an hour, or when there's a scheduling difference of more than 40 hours in a week. And the third thing that triggers this exception is when there's special pressure relationships between spaces that have to be maintained. In these cases, single zone rooftop packages would be used. An example of special pressure relationships would be in a healthcare facility or a hospital facility where you want to keep an area where there's possible contaminants at negative pressure relative to the other spaces around it. So those are a couple of exceptions that apply across the board. Laboratories have a lot of special equipment, and equipment loads can be quite high. In general, the equipment loads in the baseline building are the same as the equipment loads in the rated building, which makes them what we call neutral dependent. Modelers, however, can take credit for reductions when they can document that there's special measures taken that are going to reduce loads. For instance, if in some laboratory spaces you would need to maintain an experiment, let's say at 50 degrees. Well, one way to do that would be to have a small little air conditioner right there in the space that would that would reject heat right into the laboratory, which would have to be removed by the HVAC system. Another way would be to have this connected to the central chilled water system, in which case the rejected heat would not go into the space, but it would be rejected through the tower or the air-cooled condensers as a part of the chiller. I'm not going to go through each of these topics. I'm just going to touch on a few of them. Design conditions for laboratories tend to be a lot tighter. Heating is often 70 and cooling 72. There's also more stringent or more rigorous humidity requirements in many laboratory spaces, but these would be modeled the same between the baseline and the rated building. Laboratories also have redundant equipment, sometimes because of the risk of an HVAC equipment failure can't be tolerated. So there's redundant equipment. In general, this redundant equipment is ignored in the modeling. The only case where that might not be that rule might not be followed is when let's say you have 100 tons of load and the chiller is and the proposed design has two 75-ton chillers that sequence, and one 75-ton chiller is adequate to maintain cooling in the critical spaces. So in a case like that, the rated building can be modeled with the proposed equipment. Healthcare shares many of the aspects of laboratories. In fact, most hospitals have laboratories within them. So all of the rules of laboratories would apply to the laboratories within a healthcare facility. With regard to lighting, hospitals have many spaces, and it's often necessary to abstract and simplify the plans for modeling purposes. So there's some rules about how that's done. The HVAC rules mainly follow the two exceptions we covered earlier, one for laboratories and one for spaces that have significantly different internal heat gains or schedules of operation. Domestic hot water loads are often quite significant in hospitals, and internal loads as well. Internal loads are generally neutral dependent. Whatever is in the rated building is also assumed in the baseline building. And then finally, data centers. Most of the special equipment in data centers is also considered to be neutral dependent. That is, whatever the rated building has, so does the baseline building. These are the issues of redundancy, ventilation, humidity control, and so forth are similar to hospitals and laboratories. Data centers usually also have an uninterruptible power supply, or UPS. This is a bank of batteries and some chargers to those batteries that use energy on a continuous basis to keep the batteries charged, so that if there's a power outage, the servers can shut down in a smart way, and they can maintain power for a certain period of time. So UPS systems would be modeled as generally as a special electrical load, and it would be the same between the baseline and the rated building. The other part of Chapter 7 deals with special design features, such as the things listed here, and I'll go through each of these one by one and talk about them a little bit. Automatic window shades would include exterior blinds or drapes or something that can be either scheduled or or possibly controlled by some sort of sensor on heat gains through the space, or some combination of the two. Um, the most common way to model these is by having a schedule of multipliers on the solar gain reaching the window, or in some cases an adjustment to the solar heat gain coefficient of the window. The baseline building, of course, does not have automatic shades. Some software applications have special algorithms for modeling window shades, especially, for instance, Energy Plus, which uses some of the advanced glazing modeling tools that are embodied in Windows 5. Active chill beams are another design feature. Some software applications can model these devices directly. Most software applications can model a common induction unit, and this can be used to approximate an active chill beam. An active chill beam has a supply of air to induce air movement through the device. Another design feature are dedicated outside air systems, or DOAS. These usually can be modeled as a conventional system, either a heat pump or furnace or DX system of some sort. The challenge is that dedicated outside air systems are often used in combination with some other type of system, such as radiant heating or maybe chilled beams. And some software applications have trouble with this, but there are some workarounds that are suggested that might work in those cases. Displacement ventilation is a technique that we've promoted for schools and other applications. It's been used in Europe for decades. The air is introduced near the floor at a warmer temperature, and it rises, and you create a stratification effect. So it has a number of energy benefits. Lower air velocity, which means typically a lower static pressure and less fan energy. There's also stratification within the space, so that heat gains near the ceilings, for instance, from lights, don't really contribute directly to the heating load of the space if they're exhausted, or if the system's running on an economizer mode. So, like I say, some software can model these directly. But also approximations can be used. One common approximation is to model the lower 6 feet of the space as a separate thermal zone, and provide comfort conditions for this space, but let the space above this 6-foot zone drift into whatever temperature realm it reaches. Another technology are gas engine driven heat pumps. These are typically direct expansion compressors but they're driven by a gas engine instead of an electric motor. Software generally must have specific routines to model this equipment because there's special performance curves for part load and so forth that apply to these equipment. The gas engine creates a lot of heat, and there's an opportunity to recover that heat. So heat recovery is often a feature of these systems that would also need to be modeled. Ground source heat pumps are another advanced modeling technique. These are basically water-to-water heat pumps, or water-to-air heat pumps, and but they use the ground or sometimes a body of water uh, as the heat sink or source. These can be modeled in a number of ways. Most software applications have the capability for water source heat pumps, where you've got a condenser water loop that and its temperatures maintained, say, between 60 and 90 degrees by a boiler tower combination. You can take out the boiler and the tower and just schedule the ground temperature or the condenser, the temperature of the sink or source, and model them that way. There are many software applications that have explicit routines though for ground source heat pumps. Ice storage air conditioners are another technique. One of these is the ice bear technique. Many software applications can explicitly model this. The Energy Commission, as part of its compliance options ruling, actually approved some algorithms for modeling this type of equipment. This is what we're talking about here is a DX type ice storage system. There's more conventional ice storage systems that are used with chillers that and for those modeling algorithms are commonly available with most software applications. Radiant heating and cooling is discussed. This is often used in combination with dedicated outside air system or maybe with displacement ventilation. You wouldn't have this in the baseline building since it follows the HVAC mapping rules. Technology is switchable glazing, either electrochromic or photochromic. These are windows or skylights that change their properties, mostly the SHGC and light transmission. Some also have an impact on U factor as well. Do2, Energy Plus can all model these directly, and there can be some credit for those. Then underfloor air distribution is another topic. These also can be modeled explicitly by some software applications. They can also, like displacement air, there's like displacement ventilation, there's some stratification in the space which can be approximated by modeling the room in separate zones. The baseline building follows the HVAC mapping procedures. Then the last one I'll mention is variable refrigerant flow. These are systems where there's one compressor and condenser, but multiple evaporators each with their fans spread out through the space. With these systems, there's often many zones that can and should be combined for the purposes of modeling, just to simplify the models. To model these accurately, software needs to have explicit models because of the techniques used. I know there'll probably be lots of questions about this, so I'm gonna stop there, and we can then take some questions.